My name is Zaina Mazhar and I'm from NTS 4B. So today the topic we're going to discuss is introduction to computing, like how a computer works through a CPU, what are the relationship between the memories in a CPU or in a computer, how does RAM, ROMs and work, what are their types. So moving on, first we're going to go to the first section, which is numbering and coding. Whereas human beings use decimals, arithmetic, computers use the base binary system. In this paragraph, they're just telling that we humans use the number from decimals, which is like 1 2 3 4 5 6 7, which has a base of 10, and computers understand in a binary form, which is a 0 and 1. Then moving on, we see how does decimal and binary number system works. And here we're telling converting from binary to decimal to binary. So converting decimal to binary, we go from a division method. As you can see here, this is the remainder, and the last remainder is the most significant bit, and the first one is the least significant bit, and we assemble our answer from below to upwards. Then moving on to how do we convert binary to decimal. It is easy. It is from the power rule, like 2 to power 0 is 1, 2 to power 1 is 2, and this is the power rule which we use for the conversion from binary to decimal. Then moving on to hexadecimal, here is a table which we need to remember, because from this table we can simply convert it to hexadecimal. Here is some example how do we convert it. Simply we will use the table to convert it, or the rules we previously know. Moving on, we see the addition of binary hexa number. So this is a carry sum thing, which means in binary 1 plus 1 is 1 0, and in decimal it is 2. So 2 in binary is 1 0. So if 1 plus 1 is 2, 2 in binary is 10. So 0 is going to be sum and 1 is going to the carry. 2's complement is whatever the number we have, like here. This is the number, binary number. We're going to convert it, like whatever this number is, we're going to convert it to its opposite, but in binary system. And then after the conversion, we'll see we'll add 1 and it will turn into its 2 complements. Then here's the perform hexa addition. So simply we see all this, we'll convert it to binary, and then we'll simply get this answers. So ASCII code, this is look, this table simply defines what is an American Standard Code for information and interchange. Like capital alphabets and small alphabets have different hexadecimals. Then moving on, the digital primal means, which is basically we know as a binary logic, the binary gates. We know the AND gates, OR gate, tri-state buffer, inverter, which we have already known what is an AND gate. It simply adds the number, or it simply multiplies. Tri-state buffer, like a buffer does not change the logic gate of an input. It is used to isolate or amplify whatever the signal we get. It simply amplifies it to high or low or high impedance thing. Inverter we call it as a NOT gate. In simple words, we know it as a NOT gate, which means whatever the input it has, it is gonna just opposite it. XOR gate is an exclusive OR operation on the input. Exclusive OR produces a one output if one input is 1. If both operands are 0, the output is 0, like here. Both 0. Like what if the inputs are same, it's gonna be 0, but if they are opposite, it's gonna be 1. So this is, they are telling how carry sum is used here. As we studied previously, the carry sum thing, this is the same thing. It's not like whatever the operation or perform is gonna be the opposite of it. If 0 was 0, it's gonna be 1. If 1 was 1, it's gonna be 0. This is the block diagram and the circuit diagram. This is the block diagram and this is a circuit diagram of an half adder using XOR and AND gate. These are the two half adders which is making a full header. So these are the three full headers, like a bit adder using bits are being added by using three full headers. Flip-flops. A widely used component in a digital system is the flip-flop. Frequently, flip-flops are used to store data. Actually, flip-flops are used for storing data in this digital system world. The D flip-flop is widely used to latch the data. Notice from the truth table that a DFF grabs the data as input clock is activated. A DFF holds data as long as the power is on. Okay, this is the clock. We know it. The circuit diagram, the block diagram, and the truth table. They are saying, notice from the truth table that DFF holds the data as long as the power is on. So this is the power which is on and it is holding the data. Moving on, we get to know the semiconductor memory. Some important terminologies like how a bit is stored, what is a kilobit in bytes into the powers. They're just simply telling this here. A nibble is a half byte or 4 bits. A word is 2 bytes or 16 bits. The display is intended to show the relative size of these units. Of course, they could be composed of any combination of zeros and ones. This I already told you. Then there are two types of memory commonly used in microcomputers: RAM, which stands for random access memory, sometimes called write-read memory, and ROM, which stands for read-only memory. RAM is used for the computer for temporary storage of programs that is running. Okay, we're gonna read it thoroughly afterwards. Internal organization of memories. The internal working of every computer can be broken into the three parts: CPU, central processing units, memories, and the input-output devices. Here we see the RAM, ROM, which is the memory part. This is the CPU. This is the input-output things we can touch and see. Memory capacity. It tells us what kind of a chip has how many megabits or how much storage capacity it could hold. If we see from here an example, an article in a technical journal may state that the 128 mega chip has become popular. In this case, it is understood that although it is not mentioned that 128 mega means 128 M means 128 megabits, since the article is referring to an IC memory chip. However, if an advertisement states that a computer comes with 128 mega memory, it is understood that 128 M means 128 megabytes, since it is referring to a computer system, because according to a computer system there should be a vast memory capacity, because there are a lot of things we are storing in a computer memory. Memory organization. So this diagram tells us the memory has X address pins. This is the X, and the Y tells the data pins. A memory chip contains 2 to power X location, where X is the number of address pins. Each location contains Y bits, where Y is the number of the data pins on the chip. The entire chip will contain 2 to power X into Y bits, where X is the number of address pins and Y is the number of data pins on the chip. Memory chips are organized into number of locations within the IC. Like a microchip is organized into number, like then different locations of different numbers within the IC a computer is using. Then this table tells this is the power of 2. This tells the speed of the chips. Okay, then moving on to the ROM. ROM is the read-only memory, which is a type of a non-volatile memory that stores data permanently. If we move on further, we'll see its types: PROM and OTP. PROM refers to programmable read-only memory. For every bit of EEPROM, there exists a fuse. PROM is like, it can be used by programmer once uses a special programming device to burn the data into the ROM. Once programmed, the data cannot be changed or erased. EEPROM, erasable programmable ROM, can be erased and reprogrammed multiple times. It uses UV light to erase the data. Programming requires a special device. EEPROM, electrically erasable programmable ROM, can be erased and reprogrammed electrically. No need for UV light or special programming devices. Often used in applications where data needs to be updated frequently. Then we move on to the last one, which is the flash ROM, a type of a triple EEPROM that can be erased and reprogrammed in blocks faster and more efficient than the traditional double EEPROM, widely used in modern electronics such as smartphones, computers, and gaming consoles. So here they have given all the tables for the ROM, different kind of ROMs. Each type of ROM has its own advantages and disadvantages, and the choice of which one to use depends on the specific applications and required. Then we have mask ROM, which is MROM. Data is programmed during the manufacturing process and cannot be changed. Then we have RAM. RAM is the random access memory. RAM is a type of a computer memory that temporarily stores data and applications while a computer is running. It is called random access because the computer can quickly access and retrieve data from any location within the memory. The different types of RAM. The first one is SRAM, which is static RAM, stores data in flip-flops that do not require refreshing, faster and more expensive than DRAM, which is dynamic RAM, used in cache memory, video game consoles, and other high-performance applications. Then moving on, we have this is the block diagram of the functional block diagram from the SRAM. Then we have DRAM, which is dynamic RAM, stores data and capacitors that must be periodically refreshed, less expensive than SRAM, used in most personal computers and laptops. Here below we are given the same thing, the pin diagram, the block diagram. Then we have DRAM. DRAM organization. In the discussion of ROM, we noted all that these chips have 8 pins of the data. This is not the case of DRAM memory chips, which can have 1, 4, 8 or 16 organization. From the table, we can see the speed, capacity and organization according to the pins. Then we have bus designing and address decoding. Firstly, we have bus designing. Bus designing refers to the process of creating a communication pathway between different components of a computer system, such as the CPU, memory, and the peripherals. A bus is a system of wires that allows data to be transmitted between the components. There are different types of buses. If we read here, address bus carries memory addresses from the CPU to the memory and the peripherals. There are data bus. There are data buses that carries data between the components, such as between the CPU and the memory. Controls bus carries control signals such as read, write signals between the components. Then we have address decoding. We have read all this. Address decoding. Address decoding is the process of determining which device or memory location should be respond to a given address on the address bus. How address decoding works. The CPU sends an address on an address bus. The bus decoder receives the address and determines which device or memory location it corresponds to. The address decoder sends a signal to the selected device or memory location, indicating that should be response to the address. There are different types of address like clean address decoding, partial address decoding, full address decoding. Address decoding techniques are like from the logic gates, as they're telling simple logic gates and the address decoder using the different kinds of gates such as AND or to decode, decoders using specialized decoder chips to decode, and microcode using the microcode to decode the addresses. Address decoding is a session process in computer architecture that allows multiple devices to share the same address bus while ensuring that each device responds only to its intended address. Here they are showing us the example. Okay, now the topic is changed and which is turned to using the 74LS13838 decoder. Okay, in this it is telling it has, if we see this, it is saying that it has 3 input generates and 8 active low outputs, 8 outputs each connected to the CS pin of the memory chip, control 8 memory blocks within the single chip. It has additional inputs like G2A and G2B active low inputs. G1 is the active high input. Activation is like must be permanently activated with VCC or ground if not connected to an address signal. Moving on further, we see how does it works. Let me see one thing. Okay. Input output address decoding. Steps for input output address decoding is like we use control signals input output RN and low or RD and we are for the memory mapped input output decodes the address buses using the 74LS373 in an output design. It is like latching the data is the 74LS373 is used to latch the data sent by the CPU via the data bus. OC pin must be grounded to make the 74LS373 work as a latch. Latching section, the output of the address decoder is ANDed with the control signal low. Then it is input port designing using the 74LS244 3-state buffer used to allow data to control in through the data bus. Tri-stated refers to the 3-state buffer which can be in one of the 3 states, high, low or high impedance. Then moving on, we get this block diagram, circuit diagram of the topic we read. Now it is absolute versus linear select decoding. Absolute decoding, all address lines are decoded. Linear select decoding is only selected address pins are used for decoding. And we see these diagrams. If we have to see, like we have to choose between absolute and linear select decoding. System requirements, we have to see the system requirements as they consider the system's requirement for address space, complexity and cost. Trade-offs, weigh the trade-offs between the two methods considering factors like aliases, address space usage and circuit complexity. Then moving on, we see the peripheral input output versus the memory mapped input output. Input output communication methods is peripheral input output is isolated. Input output uses separate control signals for memory and input output. Memory mapped input output devices are assessed as if they are parts of memory. Okay, so what is the difference between both of these? Instructions. Peripheral input output uses special input output instructions, while the memory mapped uses the memory access instructions. Control signals. Peripheral input output uses the IOR and IOW, while memory mapped input output uses RD and WR. Address space. Memory mapped input output uses memory address space, potentially leading to fragmentation. Decoding. Memory mapped input output requires full address decoding to avoid aliasing, making decoding circuitry more expensive. So here the same thing with they're telling about the pins and how these LEDs gonna work after we attach gates to it. Then the CPU architecture. What is inside CPU? Key components is registers, ALU, program counters, register temporary storage for information such as data, ALUs, arithmetic logic units which performs the addition, subtraction, multiplication and divide. Instruction decoder interprets instructions fetched into the CPU, determining the steps to take. Program counter points to the address for the next instruction to be executed. Increments after each instruction. What is the functionality of CPU? Fetches the instructions from the memory, executes it according to the ALU and registers instructions. Program counters, manages the instruction sequence. Then we see we have already told the internal working of the CPUs. Harvard and von Neumann architectures. Von Neumann Princeton architecture, shared buses, code and data share the same bus. Lower processing, code and data assessed can slow each other down. Harvard architecture, separate buses, code and data has separate buses. Faster processing, code and data access can occur simultaneously. Internal on-chip, like if we see the implementations, Harvard architecture is easier to implement within a microcontroller. External implementation, Harvard architecture is more expensive to implement in systems with external RAM and ROM such as PCs. So this was all for this topic. We have understood all this in just 2 to 3 lines. So this was all for